Hello and welcome to this virtual presentation titled Multi-Stage Economic NMPC for the Tennessee Eastman Challenge Process. Thank you for joining in. My name's Tatulea-Codrean, and I'll be presenting the work done together with Jonas Fischer and Professor Sebastian Engell at the Process Dynamics and Operations Group at the TU Dortmund. When we think of a chemical plant, we think of a large-scale production process consisting of many interconnected units exchanging mass and energy with each other. We think of something like a refinery, like the one depicted in the picture on the left, or maybe a wastewater treatment plant, which is depicted here on the right. Nonetheless, when we talk about challenges in plant-wide control, we typically have to face things such as the economics of the plant, the product quality, safety and operational constraints, as well as environmental criteria, amongst others. And such an example is also the Tennessee Eastman benchmark problem, which is depicted here in this flowsheet diagram. This benchmark is based on a real process, modified by the authors, of course, but still it is a large-scale process consisting of several units. You see different ingoing and outgoing streams and recycles, and so this is a very good test case for all the challenge points that I mentioned before. That was a bit of the motivation for this talk. And in the remainder of the presentation, I would like to talk about the challenge process and about our approach to single stage and multi-stage NMPC, and then show you some results and conclusions and future work, of course. As for the benchmark process, it was introduced by Downs and Fogel in '92, and it was meant to be a benchmark problem for plant-wide control and process monitoring. It has since been used for many more other applications. It's a popular benchmark case. As far as modeling and control go, there are many works that could be cited, but we only mention here the work by Jochenheuvel, Biegler, and Wächter, since this is the one that we are also basing our model on. For the plant-wide and economics optimizing control, there are many works from our group in Dortmund and from other groups. And so the goals for this work are, first of all, to design a suitable dynamic optimizing control solution for the Tennessee Eastman challenge, and then to implement and tune this as an economics optimizing NMPC implementation. Of course, we're also interested in finding a suitable, robust NMPC structure, which we are basing on the evaluation of the economics criteria and the analysis of the impact of the uncertainty on these economics criteria. A couple of words on the benchmark itself. The diagram is depicted here again. You can see that the process consists of 4 units: the mixing unit, the reactor, separator and condenser, and the stripper. There are 4 educts. There is 1 purge stream, 1 product stream down here, and there is 1 recycle S8, which is composed of S5 and S9. The reaction taking place in the reactor is exothermic. There are in fact 3 reactions. The reactants are A, C, D, and E. There is an intermediate product and a waste product, F. The 2 products of commercial interest are G and H over here. The process model consists of 30 ODEs, describing the energy balances in the units and the molar composition for the 8 components. On top of that, we have also 13 algebraic equations, which can be computed from the ODEs, and 11 degrees of freedom. The manipulated variables for this process are the educts, these 4 streams, We also have the cooling water in the reactor jacket and in the condenser. We have the steam in the stripper, and also, as provided by the authors of the original paper, we assume that we can also manipulate the streams 8, 9, 10, and 11 directly. There are also certain sources of uncertainty, which I will get to in a while. But first of all, let's mention the economics of the plant. We are basing our work on the results, on the proposal of Downs and Fogel, with the one exception being that for the products GNH, we have taken an educated guess and set the prices to $100 per kilomole, which is considerably higher than what they suggested. This is in order to be able to perform the economics optimizing problem as we do. The modes of operation are taken from the ones proposed in the original paper. We're mainly interested in comparing the purely economics optimizing operation with different tracking operation modes. For example, the fixed flow rate in the product stream 11 or a fixed composition, a different ratio between the products G and H. Some of the disturbances that are mentioned in the original paper are also listed in this table, and you will see that not all of them have a considerable impact on the profitability of the plant. The mathematical model is, like I said, based on a set of ODEs. The entire model and all the parameters as computed by Jochen Hövell et al. Can be found in this publication. I will just give an example of the ODEs with respect to the reactor, which is one of the most interesting units in this process, and it's also where the plant model mismatch and the uncertainty affects the process the most. We also have an example of a reaction rate here. There are 3 of them, and they're all similar, and an example of an algebraic expression, in this case, the total pressure in the reactor. Let's talk a little bit about the single-stage and multi-stage NMPC implementations. When dealing with the economics optimizing NMPC of a plant-wide application, one has to deal with many constraints, both based on the safety criteria and operational constraints. One example would be the pressure in the reactor, which is not allowed to surpass a certain high limit. There's also constraints on the liquid holdups in the units and on the pressure differences between units. In this case, we have implemented all of them as soft constraints, which is a common industrial practice. We have a total of 9 constraints here. And of course, we have to translate further product specifications and operation modes into the cost function of this problem. Let's start with the economics cost function, which in this case comes down to minimizing the material use, so minimizing the amount of the EDOT streams 1 to 4, minimizing the energy spent with the steam in the stripper and the energy for the compressor, as well as minimizing the purge stream amount, S9. We are making profit in this process by maximizing the throughput, so maximizing the stream 11. In terms of tracking cost functions, we can have quadratic formulations for the tracking of a certain composition for products GNH in stream 11, or the tracking of the mass flow rate in stream 11. Of course, we have soft constraints, so we have to add the penalty for the soft constraint term, and also penalty for control movements. The multi-stage NMPC is one of the main points of this work. For those of you interested, this approach was introduced by Lucia et al. So please check out these 2 publications over here. The idea of multi-stage NMPC, put in 2 or 3 sentences, is that we are approximating the plant model mismatch by a scenario tree, by a discrete scenario tree, which branches at certain points depending on the realization of each one of these parameters considered to be uncertain. You can see that in this case, we are sampling the uncertainty interval, and we are assuming only 3 values in each interval: the lower, the nominal, and the upper value for each of the uncertain parameters. In this case, we assume that the scenario tree can branch at 2 points, and so we have a robust horizon of 2, which leaves us with 9 scenarios which have to be summed up and solved all together in one big NLP. Of course, we're also considering the option for recourse in this implementation, knowing that at the next sampling time we will get new information from the plan, and we embed this via feedback into the NLP by computing a new scenario tree at each NMPC iteration. This allows us to restrict the size of the robust horizon because we know we will always get more information in the future. Both the single-stage and multi-stage NMPC have been implemented with the DoMPC platform, which is a platform for rapid and modular MPC development. It is available on GitHub as open source software. You can find it also at this address, together with examples and the documentation of its usage. It's based on Python and makes use of Kasadi and IPOP. So it is rather efficient code and rather easy to use and to understand. Let's have a look at some results for economics and MPC. And to start that discussion, we want to look at the impact of our uncertainties. If you remember the table of uncertainties that I showed before, the impact of these uncertainties on the economics performance. We have done this in simulation tests. We have simulated the NMPC with an economic cost function for 1 hour. And we have found that not all of these uncertainties have a high impact on the total profit. As you can see here, only some of them have a considerable impact. And these turned out to be the reaction kinetics for the production of H and the A to C feed ratio in stream 4. These are labeled from here on alpha 1 and alpha 2. Furthermore, we want to investigate what is the best multi-stage NMPC implementation for this plant-wide test case. And for that, we have done more simulations with both 2 and 3 uncertainty levels for each of these 2 parameters, alpha 1 and alpha 2. And we have tested robust horizons of length 1, 2, and 3, because anyway, more than that was becoming too cumbersome for our machine, and we could not perform those simulations. In order to make a decision, we have looked at the profit, the constraint violation, and the computation time for each of these implementations. And we have found that for this case, the best implementation was a scenario tree with 4 branches, which is to say for each of the parameters, we have taken the minimum and maximum value of the realizations and ended up with these 4 combinations. You can see in this comparison that the 2-level implementation does indeed render more profit, and it takes considerably less time to solve. As for the results, I will be showing you results with 2 control modes. The first one is the purely economics optimization, and the second one is a combination of economics optimization with composition tracking in stream 11. For the single stage NMPC, we are using the nominal values of the parameters, and of course we have a prediction horizon of 2 hours sampled with 200 seconds prediction step. You can see that for the first 3 hours, the economic profitability reaches its highest, and you can see also that the process is driven to its limits. The pressures are at their upper bounds. Also, the feeds are at their upper bounds, and the liquid levels. So we can assume that this economics operation is indeed the most profitable. After the control goal switch, the feed ratio changes as it was prescribed by the cost function, and from hour 5 on, you see that we are producing more H than G, and the profitability is slightly lower than before. The multi-stage economic NMPC was simulated with a detrimental parameter combination, as you can see here. You see that the profit is slightly lower, but that is to be expected because the multi-stage NMPC is inherently more conservative and it computes an automatic back-off from the constraints. But nonetheless, you can see that the constraints are satisfied and we are paying the price in terms of seconds per iteration. This optimization is slightly slower. Of course, we have 4 scenarios to be solved in this compared to 1 from before, and also the profit is slightly lower. The last simulation is, again, a multi-stage NMPC simulation, but this time the uncertainty structure changes for the real plant every hour. You see that this poses some challenges to the optimizer, but the constraints are always satisfied, and the price to pay in the average iteration times is not so high. All of these implementations would still be real-time feasible considering a sample time of 200 seconds per step. Coming to the conclusions, I've shown you a implementation of plant-wide optimizing control for the Tennessee Eastman challenge process, which is, to our knowledge, the first instance of economics multi-stage NMPC applied to such a large-scale process. You've seen that this process can be successfully controlled with only economics criteria, and you have seen a method for selecting a multi-stage NMPC implementation for a plant-wide control. We have also successfully demonstrated an application of plant-wide control with the DoMPC platform under different modes of operation and in different simulation test cases. Of course, there is always a lot of work to look forward to, but we are confident that multi-stage economics NMPC is feasible for a process of this complexity, and we will continue development in this direction. Thank you very much for your attention. I look forward to your questions. Thank you.